Next up is the definition of minimum and maximum. And again, those are some intuitive terms in the English language, but in math we would like to give them some actual definitions that rely on symbols. So we call something a minimum when the following is true. So suppose we're talking about a number c. We say that the number c is a minimum if the y-coordinate, so f of c, is smaller than f of x, meaning every other y-coordinate on the graph. So like for example, if you have a function that has c right there and c has a y-coordinate over here, but every other y-coordinate on the graph is bigger than this, then obviously the c is the bottom of the hill. We say that c has a minimum. Now what about a maximum? We say c is a maximum when the following is true. If the y-coordinate of c, so f of c, is greater than every other y-coordinate on the graph. So like for example, again, suppose that this is the xy plane and you have c on the x-axis. You look at the y-coordinate and it's the highest one ever. So it's always the highest one. So it's bigger than this y-coordinate and that y-coordinate and that y-coordinate and so on and so forth. So the graph kind of looks like an upside down U. So that tells me that the y-coordinate of c is the biggest y-coordinate. So that's f of c. Since it's the biggest one, we say that c has a maximum. Typically speaking, a minimum or a maximum will occur at a critical value. So if you want to find a minimum or a maximum, just find a critical value and you would have found yourself the minimum or the maximum. So another way of saying this is to say that a minimum or a maximum will be found where the derivative is 0 or the derivative is undefined, does not exist. When you hear the word extrema, you should think to yourself that somebody's asking for the maximum and the minimum of a function. So again, that's great and everything, except how do we do this in reality? How do we find the maximas and minimas in reality? Well, we pretty much will be doing what we did in the last example. We will find the derivative, find the critical numbers, draw the horizontal line, put the pluses and minuses, and then look at the pluses and minuses to figure out where the maximum and minimum are. That's what we call the first derivative test. That's what you're seeing in this box, basically. It's describing those steps. So you will end up with a minimum where a switch happens from negative to positive. So on the line, if you have a negative first and then a plus after, the number in the middle is going to be called a minimum on the first derivative test. Now, however, if the other thing happens, if you have a positive first, then a minimum afterwards, you will end up with the number in the middle being called a maximum. What's the reason for this? The reason for this is the following. If the function is decreasing, then increasing, well, that creates like a little valley. So that we know the middle is going to be a minimum. The second situation, the derivative is positive, which means the function is going to be increasing. Then the derivative is negative, which means the function is going to decrease. So it creates a little bit of a hill. So that means the number in the middle is going to be a maximum. So that's what the first derivative test for relative extrema is telling us. So let's take a look at this. Example 3 says, here's the function. Again, it's the same function from the previous examples. And it wants the maximum and it wants the minimum. Maximum and the minimum. So what I want to do first is write down the function, then the derivative, then find the critical numbers, then do the horizontal line with the pluses and minuses on it. We did that on the last example, so all I have to do really is just copy it over. So this is what it looks like so far. And I often joke with people telling them, if you don't know what to do in this whole chapter, chapter 2, then just find the derivative, find the critical numbers, put it all on a horizontal line, find the pluses and minuses, and you'll be 90% done with every possible question that could be asked in this whole chapter. So the standard procedure is like this. Start with the function f of x, find the derivative, find the critical values, then draw the line and put the pluses and minuses on top of it. And the next step could be a little bit different, but that's the only step that changes. So in this particular problem, they wanted to find the maximums of this function. So all I have to do is finally look at the intervals, right? So the first one is positive. So that tells me that the function f of x is actually increasing. So I'm going to put arrow up. That means it's increasing. So because the derivative is positive, the function is increasing. Now the middle interval, the function f of x is going to decrease. Why is it decreasing? Because the derivative is negative. Having a negative derivative means that the function is going down. Then finally, on the third interval, the function f of x is going to be going up again for the same reason that we had on the first interval. When the function's derivative is positive, the function itself will be going up or increasing. So all I have to do now at this point is look at the plus minus situation that I made. So think about it like this. I went up, then I went down. Well, that creates a little bit of a mountain. So that means -1 has what we call a maximum, because we went up before it, then we went down after it. So my little stick figure guy was going uphill, then afterwards the little stick figure guy was going downhill. So that creates a mountain, and that's the peak of the mountain, so that's why we call it a maximum. Now on the other hand, in the middle interval, the function was going down, just like we said, then it went up after the number 2. So it went down all the way to 2, and then it went up after 2. So then again, that creates a little bit of a valley situation. So right, the graph is looking something like this. So it's a valley, which means that 2 itself has a minimum. Now in both of these cases, these maximum and minimum that we have are actually relative max and relative min. So there's a difference between a relative maximum and a relative minimum, and an absolute maximum, absolute minimum. So let me explain real briefly what the difference is. If I have a graph that looks like this, for example, this point right here is the lowest point always on this whole graph. We use the word absolute minimum to describe this. It is absolutely the lowest point ever on the whole graph. So that's why it's called absolute. Now there are situations where this happens. You get graphs like this, where this down here is a minimum. However, it is not the lowest point. For example, if you extend this graph a little bit down, all these points right here are going to be lower than the minimum. So in this case, we call this a relative minimum. So relative because in its own little world, it is the lowest point. But if you look at the rest of the graph completely, then it will not necessarily be the lowest point on the whole graph. So that's why we call it a relative minimum. And the same situation applies with absolute maximum, absolute minimum. So if your graph looks like this, and this is the highest point always, we say absolute maximum. However, if my graph looks like this, then this point right here is called a relative maximum. And again, it's a relative maximum because other points on the graph, all these guys over here on the side, are going to be higher than it. So it's not going to get the privilege of being called absolute maximum. So by doing what we just did, we actually answered parts 1 and 2 of the problem. So here we go. Let's go ahead and finish it off. So in part 1, they said, where is the relative maximum? So I'm just going to write down x equal to -1 is a relative maximum. And for part 2, typically I would have to copy everything all over again, but don't copy it. Since it's already been done once, all you have to do is write down that x equal to 2 is a relative minimum. And that's basically the end of the question, parts 1 and parts 2. Now, oftentimes they will want the y-coordinate of the point. So they are going to ask you for the x and y coordinates. How do you find the y-coordinate of the point? Since x is -1, to find the y, all you do is plug -1 back into the original function. Be careful not to plug it into the derivative. If you did, you would get 0. That's how we got it in the first place. So if you want the y, put the x into the function. So again, if you want to know how low this minimum is, you take the 2 and you put it into the function. So I'll just write it in a faint notation on the side. I'm writing put x equal to -1 into the function f of x, not into f prime, to get the y coordinate. And same thing again for the 2. So if you're interested in the y coordinate, you put the numbers into the function f of x. Now part 3 is saying to graph the function. And again, we just want a quick sketch of the graph. I'm not looking for perfect accuracy. If I wanted that, I would just use a calculator. But, you know, let's kind of imagine what the graph looks like. So first of all, here's the xy plane. So let's draw that. And next, we have to locate the maximum and minimum. So we have a maximum at -1 and a minimum at 2. So the function was highest at 1 and lowest at 2. And keep in mind, because of the line that we drew, the function was always increasing before -1. So when you draw something, you have to draw something that always increases before the point -1. So that's kind of looks something like this. A function that always increases may look something like that. So it starts down at -infinity, and my little stick figure guy travels uphill until he reaches this point right there. At that point, he's standing at the maximum location. That's what we discovered on the line. Then he starts going downhill from -1 all the way to 2. So, okay, he's going downhill from that red point to the red point right there. So maybe something like that. Or, you know, you could try to make it a little bit more bendy, whatever. Doesn't matter. We're not looking for perfect accuracy. We just want to get an idea that the graph is doing that. And again, if my little stick figure guy is traveling along this path, he's going to be going downhill. He gets to the minimum, and at this minimum, things are going to turn around because the function becomes positive again. The derivative becomes positive again, which means the function is going to be increasing. So again, the function increases on that interval. And again, my little stick figure guy would have to start climbing uphill at that point. So that's the sketch of the graph. I hope that made sense.